Now, as an example, I've got two examples. Let's calculate the transformation of this continuous time signal with the transformation given by x of 2t minus 1. So there are a couple of different things going on there. There's a scaling of time by a factor of 2, and then there's a shift minus 1. There's a shift by 1 there. And then we're also going to look at a discrete time case. Take this signal and calculate its transformation 1/2 x of minus n plus 1. So there are three things going on there. The 1/2, the minus 1, and the plus 1 there. Anyway, let's go back to the continuous time, and let's work on trying to figure out, all right, let's sketch g of t, which is the transformation. So I'm going to try to sketch that. So here are my axes. Here's t-axis, here's the origin, and this is going to be g of t. Now what I can do is just plug in some values of t and kind of get a feel of what we're dealing with. So for example, if I plugged in t equals 0, then I would have g of 0 equals x of minus 1. Okay, well, what is x of minus 1? Well, I look over here. Here's where minus 1 is. So x of minus 1 is 1. So now on my graph, g of 0 is x of minus 1. So g of 0 is 1. Right there. Okay, so this point here got mapped to this point here in the transformation. All right, that's kind of cool. Let's plug in another value of t, maybe g of 1. Okay, so t equals 1. G of 1 is equal to x of 2 times 1 minus 1. So that would be x of 1. So what is x of 1? Well, I look over here. X of 1, ooh, that's about, that's about right here, 1/2. Okay, so that's going to get mapped to, that's g of 1. So here's 1. So that will be 1/2, you see. So that gets mapped to this here. So you might have a decent idea of what's happening, but let's try to be a little bit more careful with the values we plug in of t here. So the values we're choosing for t. Now, I want to find where is this edge in the new plot. In the old plot, or the input, that edge is at minus 2. So I would like to have x of minus 2 here. X of minus 2 is this edge. So what value of t gives me minus 2 here? And so that looks like t equals minus 1/2, I believe. So if we plugged in minus 1/2 for t, that would give me x of 2 times minus 1/2 is minus 1, and then another minus 1, x of minus 2. Well, that's exactly what I wanted, because x of minus 2 is this edge. So now in the new plot, in the transformed plot, x of 1/2, excuse me, g of minus 1/2, so maybe minus 1/2 is like right here. That's where the edge is. Okay, there's minus 1/2. That's where the edge is at. Interesting. So let's continue being careful with our choices of t. And now I'm going to try to find this elbow here where the plot starts to decrease. So that's x of 0. That happens at the origin, 0. So what value of t must I plug in to get x of 0? Well, that looks like 1/2. Because 2 times 1/2 minus 1 is x of 0. So let me plug in 1/2. So I would have g of 1/2 equals x of 0. Okay, so now I know the elbow on my graph happens at 1/2. So here's 1/2. So I've got something like this, and now it's going to start to decrease. And then finally, let's try to figure out where this elbow is at. Okay, that's x of 2. So what value of t must I plug in to get 2 here? And that looks like 3/2. G of 3/2 is equal to x of 2. And so at 3/2 might be like right here. I have that elbow, and so my signal, then I can fill in all the other kind of gaps, the values we did not test. And here on the right, this is my G of t. This is my transform signal. I'm going to overlay that on the original plot. So let me do that. So this would be 1/2 is kind of right here. It goes like this, and it goes straight to about 1/2 there, and then it kind of comes down like this. Okay, and so this is the new plot. So two things have happened here. One, we have a time compression. The width of this signal, it used to be, from -2 to 2. So it used to be 4. Now it's -1/2 to 3/2, right? Because this was 3/2, we said. -1/2 to 3/2. So that's 4/2 or 2. So the width used to be 4 from -2 to 2. Now it's 2, and that's due to this 2 here. It's been compressed by a factor of 2, and then we also shifted it. We shifted it, and we shifted it to the right, and that's because we're subtracting a positive number. So that is what caused the shift there. All right, good. Now let's take a look at our discrete time signal down here, x of n, and we're going to apply this transformation. G of n equals 1/2 x to the x of minus n plus 1. So let's plot that. All right, so here's going to be my origin, and notice the origin on the original plot is right here. All right, so I can just plug in values of n. So G of 0, so n equals 0, is 1/2 x of 1. So x of 1 is this guy, 2. So 1/2 of that is 1. So I need a 1 right here. G of 0. And you can kind of continue on like that. Let's plug in n equals 1. So G of 1 equals 1/2 x of 0. X of 0 is this guy, 1. So I need 1/2 of that. So that would be 1/2. And that's G of 1. So that's the first sample. And if I plugged in G of 2, or n equals 2, then I have 1/2 x of, so with n equals 2, this would be minus 1. So x of minus 1 is 2. That's this guy. So 1/2 of that is 1. So I'd have a 1 right here. 1. So this is 1/2. This is 1. Okay, and maybe you see what's happening here. If I plug in 3 for n, I'm going to get this sample here. Let's check it out. 1/2 x of minus 3 plus 1 is minus 2. So this is the minus 2 sample. And so that's a 0. 1/2 of that is also 0. So I've got this. And I continue on like that. The next sample, so this is 1, 2, 3. The next sample at 4 is going to be half of this sample here. So it's going to be minus 1/2. And the fifth sample is going to be half of this sample, which is minus 1. And we'll get zeros. Okay, and then if I go the other way, let's say I want G of minus 1. So I plug in minus 1 for n, I get 1/2 x of 2. X of 2 is a 0, this guy here. So I get a 0 here, and I'm going to get a 0 here, and then I'm going to get 1/2 of this sample, -1/2, and then a 0, and then a 1/2 of this sample. This is what I've got. This is g of n. So notice a couple things here. First, the signal has been reversed in time. So you can tell that by, you see this feature here? How it goes from -1 to -2, that's now over here. So there's been a sort of a flip that's happened, right? And that flip is due to this negative 1 in front of the n. That was a time reversal. Then it's also been shifted. Okay, notice that our kind of in between 2 and 2 was the origin here, and in between 1 and 1 is here, and that is not the origin. That's off by 1 unit, and that is due to this 1 here. That's shifting our graph. Then all the samples were scaled by 1/2, and the reason they were scaled by 1/2, well, that's due to this here. All right, let's look at another example. Again, feel free to pause the video if you like. Let's say I have another discrete time signal, and the origin is there. Let's say it's 2, then 1, then 0, then 1, and then the rest zeros. And let's say over here we also have 1, 0, 1, and the rest zeros. Okay, this is x of n. And I'm interested in the system that reverses it, x of minus n. I want to figure out what that transformation is. Draw g of n that is a flipped version of x of n. So notice here something interesting. I'm going to draw g of n. If I want to know g of 0, so I plug in 0 for n, well, x of 0. Okay, so they're equal at the origin. G of 0 is x of 0. So that's a 2. That's a 2. So here's my origin. I'm going to draw 2 right there. All right, now let's say I want to know g of 1. So I'm going to plug in n equals 1. G of 1 is x of minus 1. Well, x of minus 1 is 1. So I've got this. But also, notice, if I wanted to know what g of minus 1 was, that's x of 1. Well, that's also a 1. Right, because x has this sort of symmetry that at minus 1 we have the same value as we do of x of 1. So those have been reversed, but we get back the same signal. And we are going to find out that when we plug in n equals 2, g of 2 would be x of minus 2. Right, so that's this sample here. So that's going to give us a 0, and then if I wanted g of minus 2, that would be x of 2, which would be this sample. So that would be this guy here. And you see, after the transformation, I get back the same signal. See that? X of n is equal to g of n. And that is, of course, due to the symmetry of the signal x of n. Notice that if I start at the origin and I go to the right for positive n, I get the same thing as if I start at the origin and I go to the left for negative n. That's called an even signal, and we'll have much more to say about even signals later in the course. But if you reverse an even signal, you get back the same signal then, due to the symmetry. Okay, finally, let's look at one last example. An equation. Let's say x of t were 2e to the negative 3t. Okay? And we're going to send that into a system that does the following. Let's say it produces, not of n, g of t, it produces 1/2 x of minus t plus 1. Okay, can we write an equation for g of t? All right, so g of t is 1/2 times a reversed x shifted by 1. So this would be g of t is 1/2, and then I'm going to put in minus t plus 1 wherever I see a t in x. So I've got the 2 from here, e to the minus 3, and I'm going to put a minus t plus 1 there. And the 2 and the 1/2 cancel, and I get negative e to the 3t minus 3. Okay, so in a system that reverses t, shifts by 1, and scales everything by 1/2, if we put in 2e to the minus 3t, then what we get out is e to the 3t minus 3.